Welcome to the review of operations with polynomial expressions. Before we can get started with the actual operations of adding, subtracting, multiplying, and dividing by a monomial, because that's the only case we're going to cover in this review, we need to first make sure we all are up to date on the terminology of polynomial expressions. So a polynomial in a variable x is a finite sum of terms of the form ax to the nth, where a is a real number called the coefficient of the term, and n is a whole number exponent. So just to give you some examples of things that are polynomials, it could be something as simple as just 2x squared plus 5. It could be -7. It could be something complicated like -3x to the 5th minus 42x to the 4th plus 37x to the 3rd minus 7x squared plus 2. I didn't do all the powers, but you get the point. It's just adding and subtracting terms together that have numbers, variables, and powers. And that's it. That's what a polynomial expression is. So you could even have things that have multiple variables. I'm just making up numbers, but -3x squared y squared plus 7xy minus 3. We typically write our polynomials in descending order. That means highest power down to lowest power. When you get into things like where you have x and y both, I usually use the general rule of exhaust the x's from highest to lowest because they come first alphabetically. It's like if you have matching terms. So say you had, an x to the second and a y to the second as two separate terms, we would typically write the x to the second first because of the alphabetical order. We don't get too hung up on that, but it is something that we typically do. A monomial is a polynomial that has exactly one term, so something like -2x squared y. Even though there's multiple things happening here, it's a single term because there's no adding or subtracting connecting it to another term. A binomial is one that has two terms exactly, so x squared minus 5. That's a binomial. A trinomial has exactly three terms, so 2x squared plus 7x minus 5. So that's just different special cases. Anything that has more than three terms, we just generically call it a polynomial. But monomials, binomials, and trinomials are also polynomials. So just make sure we have that. Each term of a polynomial has its own degree. So you just look at the individual term and you look at the variable pieces. This is x to the second, so this term would have a degree of 2. This term has an x to the first, so it has a degree of 1. The final term in that trinomial had no x's, so it has a degree of 0. So the sum of the exponents on the variable contained in the term. Now the reason they say the sum there is because you will have things like this, 2x to the third y squared minus 7x to the second y plus 5x plus 2, okay? This has multiple variables in each term, so you add the different exponents together to define the degree of the term. That doesn't mean you're combining the x and y together to make one variable. You're just trying to figure out how many powers do you have on the variables in that term. So this would be like a degree 5 for that specific term. This would be a degree 3 for that specific term. This is degree 1, and this is degree 0 because there are no variables. Now that's important to note because the degree of the entire polynomial is the greatest degree of any term of the polynomial. So you have to look at all of the terms you just defined and say which one had the biggest power. The biggest power that we saw in that example was degree 5. So for the previous example, right above, then we know that the degree of the entire polynomial is 5. So that's important to note. Now, to talk about the actual operations, we need to talk about what are going to be our steps to simplify these expressions. If you're adding and subtracting polynomials, it's going to work pretty much like terms. In fact, adding, you directly just start adding like terms together. Remember to add two like terms together, so say 2x squared plus 4x squared. You don't do anything when you're adding or subtracting to the actual x's. Remember, you're just making sure that they have the same x and the same power. We're combining the coefficients, the numbers in front. So this would be 6x x to the second. So remember, when you're adding or subtracting, you should just be looking at the coefficients after you've determined the like terms. Subtracting is a little different. You have to change the signs of the polynomial that's being subtracted. You'll see an example in a minute where we see a polynomial minus another polynomial. The second polynomial needs the negative or subtraction distributed throughout. Then we will add like terms. So essentially you're changing this to adding the opposite. To multiply two polynomials together, we will apply what we have learned about exponents and the distributive property. Remember, the distributive property says, and this is a property that would have been covered typically in a previous class, but it says that you multiply whatever is, so you have a times connecting a term to a binomial, trinomial, some type of polynomial. There's adding or subtracting inside. What we do is we multiply the term out front times each different term inside. So this becomes AB plus AC. So we will use that to help us multiply polynomials. If you're just doing two polynomials, you multiply each term of the first polynomial by each term of the second polynomial, and then you combine your like terms. And remember, we didn't physically define this since it's previous knowledge, but like terms means they have the same variables with, important here, same matching exponents. So an x to the second and an x to the third have the same base, but they're not the same exponents. I typically don't teach a lot with FOIL. It's a shortcut to multiplying two binomials. I mean, we'll go through it with one of the examples just to remind you of what FOIL is. It just tells you the order to multiply in, first pair of each binomial times the outside binomial pieces times the inside pieces of the two binomials, and then the last piece of each binomial. Because you can do this specifically using distributive property, there's no need to actually memorize FOIL, but it is a useful tool that most people know. The reason I don't always stress it so much is because when you do a binomial times a trinomial, you're not using FOIL anymore. You're going to need more multiplication going on. If you're squaring a binomial, it's very important to write the binomial twice. Do not try to put that 2 on the outside as something you're applying to the bases inside. That rule was only good when you're multiplying inside the parentheses. So we are going to write the binomial twice and distribute and simplify. Notice there is a middle term when you do this. You end up getting a trinomial with a middle term. If you're multiplying the sum and difference of two terms, you're going to distribute and simplify. What we mean by that is you have a binomial and an identical binomial where the only difference is the sign in the middle is different. So a plus versus a minus. When you distribute or FOIL that out, you end up getting middle terms that cancel, and you're left with just a squared minus b squared. So that one will be more important to us when we go backwards when we're doing factoring, but you can still do it by distributive property. And then finally, the last operation is dividing polynomials. You divide each term of the polynomial by the monomial in the bottom if you're dividing by a monomial. You just split it up into separate fractions and you do the division. You could do it by long division, but it's a little bit of an overkill in this situation. If you're dividing by something bigger than a monomial, so a binomial or higher, you have to use long division. And that is not in this review because it is actually something we teach as part of this course. So it'll be coming later. So let's look at our first example here. It says express as a polynomial. So we're just supposed to simplify it down. So it looks like we have a parentheses indicating that we have a polynomial right here, and we have a second polynomial here. And they're separated by subtraction. When you're subtracting, I like to think of it as adding the opposite. So the first polynomial, and you don't need the parentheses, it's just to emphasize that the polynomial is there. So if it's adding or subtracting, we end up dropping the parentheses pretty quickly. So we bring all of those first terms down. This says do the opposite of everything in the second parentheses. So that's a positive 7x cubed, so we'll actually make it a negative 7x cubed. You can think of this as distributing -1. This was a positive x, so we'll make it a negative x. This was a -5, so we make it a positive 5. So we change the signs of that entire second binomial, or excuse me, polynomial. Then we look for like terms. So I always start with my highest power first, 5x to the 4th. Has no friends, no like terms, so it's just going to come down. We look at the negative 3x cubed. There's also a negative 7x cubed. When you see like terms, you keep the x cubed here, but we actually combine the coefficients. So that would be negative 10 x to the third. The positive x and the negative x are opposites of each other, so they're actually going to cancel each other out. And that's also going to happen for our negative 5 and our positive 5. So we actually got two things that canceled out here. Now, if this had been a positive 5 as well, then we would have ended up having positive 5 and positive 5, which would have been positive 10. So don't cancel unless they're opposite signs of each other. So actually, this is the final answer for that one. So it worked out pretty nice. Let's look at part B. We are dealing with multiple operations all in one problem. There is multiplication right here. So we're going to be timesing. There's also multiplication right here. And then there's subtraction in the middle. Now you still have to treat this, and this is why order of operations is very important. We still have to treat this by the order of operations, which means we multiply before we can subtract. So when you're multiplying two polynomials together, you want to make sure that you multiply everything that's in the first polynomial by everything in the second. So this 2y needs to be multiplied by y and by 1, and the negative 3 needs to be multiplied to the y and to the 1. So if I write that out, and I'm going to just show all my steps, this would be 2y times y plus, because every time you go to a new pairing, you have a plus or a minus depending on the sign you're going to get when you multiply, but you have a separate term, 2y times 1, and then we'll have negative 3 times y and negative 3 times 1. So that has now been completely distributed. On this one, we also need to distribute, and I'm going to go ahead and take that negative with it as I go. So we're going to take care of that negative sign right now. So we really are kind of doing the subtraction step coherent at the same time with this one. But this would be negative 6y times y and negative 6y times negative 2. So what you notice down here is that I have lots of little groups of multiplication that are separated by either adding or subtracting. So I need to multiply all these before I can look for combining like terms. So 2y times y would be 2y squared. 2y times 1 would just be 2y. Negative 3 times y is negative 3y. Negative 3 times 1 is negative 3. Negative 6y times y is negative 6y squared. And negative 6y times negative 2 is positive 12y. Something to note here. During this step, when you're distributing and working something out, this is when it's possible for an exponent to get bigger. When you are multiplying two bases together that are the same, remember we add their exponents. That's why this ended up being a y squared. We've already done all of our multiplication, so none of our powers should change again from this point because we've multiplied everything we could. Everything after this is just adding like terms, so we should only be focusing on are they like terms and combining the coefficients. So I do have that a y squared, I have those two different ones that are like terms. So 2 minus 6 would be negative 4 y squared. For the y's, I have a 2y minus a 3y and then a plus 12y. 2 minus 3 is negative 1, plus 12 would be positive 11y. And then negative 3 has nothing to combine with, so it's just going to come down. And that is my final answer. Okay, so let's look at C. C is a binomial times a trinomial, so we are distributing. FOIL would not work here because it's not two binomials, so we need to distribute 3x to everything in the second parentheses, and then we'll need to distribute negative 5 times everything. Now obviously you get to a point where you don't need to write all this out. This is a review video, so we're kind of going through some more of the grungy work and having to show all of our steps. Most people can get to a point where they just do this multiplication in their head, but it never hurts to slow down and just review. So 3x times x squared plus 3x times negative 2x plus 3x times 4. And then we're going to have negative 5 times x squared, and then negative 5 times negative 2x, and then negative 5 times positive 4. Notice again, we have, because this was a 2 by a 3, we're going to end up having 6 different multiplication groups down here. If it was a 3 by 3 trinomial times trinomial, we would end up with 9 different multiplication groups. So this is 3x to the third. Because we are multiplying, we get to add our exponents when the bases match. This would be negative 6, x times x would be x squared. 3 times 4 would be 12x. Then we get negative 5x squared. Negative 5 times negative 2x would be positive 10x, and then negative 20. Before we can say we're done, we need to look for like terms that we can combine. 3x cubed has nothing to combine with it, so it'll come down. The x squared, we do have a combination here. That is going to be negative 11x squared. We have 12x and 10x, so that's going to be positive 22x, and then bring down the minus 20. Final answer. Okay, for D part, we have a dividing by a monomial. So we're going to split this up since this is one term on the bottom. There's no plus or minus down there. We're dividing by a monomial. When you're dividing by a monomial, you can think of it as separate fractions. You just split them up based on where the subtraction or adding happens on top. So this is 9c to the fourth d to the third divided by 6c squared d squared. Minus, because we have that minus sign there. If we had a negative on bottom as well, we would have to consider our sign being a combination of both of those. But for us, we just have a plus on the bottom. So write our second term on top over the denominator. So you're just splitting this back up into 3 separate fractions. And then plus 6c over 6c squared d squared. Okay, so now that we've done this, we can reduce each individual fraction. So 9 and 6 are both reducible by 3. So that would be a 3 on top and a 2 on bottom. There are 2 c's on the bottom that can cancel out with 2 c's on the top, so that's going to be c squared. 2 d's on the bottom that cancel with 2 up there, so that's just going to be d to the first. So this first term is 3c squared d on top all over 2. So there's my first term. For the second one, 6 and 15 are both divisible by 3. Again, so that's going to be a 2 and a 5. C's, we have 2 on bottom that cancel with 2 at the top, so that's just going to be c to the first. And then the d squareds match exactly. So this one will be minus 5c to the first over 2. And then plus, the 6's are going to cancel completely, and one of the c's cancels not with the top part. The top part's going to be gone, but the bottom one will still have a c to the first. So this would be a 1 on top since there's nothing up there that didn't cancel out over c to the first d squared. Now you could try to combine these first two, but that's not going to give you anything really nice on top because these are not like terms on top, but you could make it one fraction if you wanted to. I'm just going to leave it as is. So there it is. All right, for E, we're looking at a binomial times a binomial. So you could just distribute here or you can FOIL. So just to remind you of what FOIL is, you do your multiplication and labels. So first term times first term. Then we do outsides or outers, so outer terms together. Then we do inner terms together. That's the ones that are closest to the middle parentheses. And then we do last position in each binomial. That is essentially just the distributive property. The only thing you have to be careful here is that you have to make sure you're actually multiplying in between. If this was a plus sign in between these two parentheses, you do not need to FOIL. FOIL is only for multiplication. So this would be a squared times a squared, so that'd be a to the fourth. A squared times negative 9 would be negative 9a squared. 1 times a squared would be positive 1a squared. And 1 times negative 9 would be negative 9. So that's first, outer, inner, last. We combine the like terms, and that gives me negative 8a squared in the middle. So there's the answer to E. Okay, last example is going to be squaring a binomial. A lot of students will miss this specific example because they try to square everything inside. Remember, that's not true if there's adding or subtracting inside. That's only true if everything is multiplying or dividing, or multiplying and dividing is okay as well, but no adding and subtracting. The best way to keep yourself from making this mistake is to always write a binomial squared as a binomial times itself. So write it twice and FOIL, or distribute. Which, remember, since it's two binomials, it is FOIL. Okay, so let's multiply this out. 3x times 3x is going to be 9x squared. 3x times 4y squared is going to be 12xy squared. We get 4y squared times 3x, so that's going to be 12xy squared. And 4y squared times 4y squared is positive 16, and then y squared times y squared is y to the fourth. Notice that our middle terms are still here. They don't cancel out. They actually are the same, so they add together. So it's 24xy squared, and then plus the 16 y to the fourth. So that is my squaring of that binomial. I thought there was another example on here. I'm going to make up another one really quick because there's one missing. Okay, in a final example, part G, we need to FOIL or distribute this out. So this is 2x plus 3 times 2x minus 3, so two binomials that look pretty much identical except for the sign in the middle is different. So when we go to distribute this, this would be 2x times 2x, which is 4x squared, 2x times negative 3, which would be negative 6x, 3 times 2x, which would be positive 6x, and 3 times negative 3, which would be negative 9. When we combine the like terms, the middle terms will actually cancel out, and we're left with two perfect squares that are being subtracted. So 4x squared minus 9.